For Unit 3, we're going to shift away from vectors and vector-valued functions into functions of several variables. Now, in the third edition of the book, this is actually a mixture of some pieces of sections 13.5 and 13.6, as well as chapter 15 put together. But if you're in the second edition of the book, this is chapter 12. All right, so looking at the first section, right here is where we're going to begin. Section 12.1 in the second edition, or a piece of 13.5 and 13.6 from the third edition. Either way, it's graphs of multivariable functions. Now, let's think back to algebra and pre-calc and calculus 1 and calculus 2, right? All of those courses we had, they all used y equals f of x as a notation, where your input, your independent variable was x, and your dependent variable is y, which is f of x. And then in the last unit, we learned that, and this was chapter 11, if you're in the second edition, we learned that, well, we can define this a different way. We can take t as our input, and we can either have a two-dimensional or a three-dimensional vector-valued function, and it will create a curve through space, right, at time t. And so either x and y or x, y, and z are our variable or our output variables, depending on whether we're two-dimensional or we're three-dimensional. All right, now we're going to do something a little bit different in this unit. What we're going to do is, and this is chapter 12 in the second edition, we're going to take x and y as our inputs and get a new curve z, or surface z, I shouldn't say curve. Or we can take x, y, and z and get a new function. Sometimes, usually we call it w. So this is two-dimensional. You're taking a two-dimensional point and getting out a third piece or component, right? A z value. Or you're taking a three-dimensional point and getting out a fourth component. Fascinating. All right, and we will see how all this works throughout this unit. All right, so let's begin with example 1, which is just a simple substitution example. Do you know how to read this, right? So we have f of xy, where it is equal to x squared plus 3xy minus y squared. And all they want us to do is find 4, 3, and interpret in the context of a graph. Okay, so f of 4, 3 is equal to 4 squared plus 3 times 4 times 3 minus 3 squared. Now, of course, we could find that value with a calculator, but that's kind of boring. So I found it in Maple here. So I named my equation E1, which is x squared plus 3 times x times y minus y squared. And so it just knows that it's named that. And then I asked it to substitute the values, x equals 4, y equals 3. Notice I put that in brackets, into E1. And it tells me the value is 43. So therefore, I know that this is 43. Now, keep in mind, it asked us to find f of x, y, and so that is z right here. So z is f of x, y. Just like y was equal to f of x, z is equal to f of x, y, right? It's your output. All right, so then we want to interpret this value in the context of a graph. Well, we don't have the graph, but we do know that the point 4, 3, 43 is on the graph of this function. Even though we don't really know what it looks like yet. All right, so we want to start building up our arsenal of multivariable functions that we'll just know by looking at their equations what they are. So we're going to begin by looking at planes. Now planes, well, you know what they are, right? Two-dimensional surfaces that have length and width but no height, right? So what would the equation of a plane look like? Let's think about the geometry involved. Now if we know a point, x0, y0, z0, we'll call it P. So I'm going to call that point right there, that's P, which is x0, y0, z0, is on this plane. And we also know a vector that is perpendicular to the plane, which is the normal vector, n, which I'm going to have be green right here. So the normal vector n is this vector right here, sticking up out of that point P. So that's n. Now, why is it sticking up out of that point? Well, remember, vectors are free. They can kind of stick up out of whatever point you want. All right, so we want an equation for all of the sets of points, x, y, z in the plane. Well, then if you had a, let's see here, a direction vector here to get from this point to any point on the plane, right? I'll call that direction vector v. And then that point q will be a point on the plane, x, y, z. So I'm going to call this point q, right? Q. So q is x, y, z. Well, what we're going to do here is a little bit analogous to a point slope form of the equation of a line. Let me figure out, first of all, what my direction vector v looks like, right? Because direction vector connects the point P and the point Q. And remember, a direction vector is, well, any vector is terminal minus initial if you have the 2 points. So that would be terminal minus initial, right, for all 3 components. So the terminal point is x, y, and z. And then we would subtract away the initial point, which is x0, y0, z0. Okay, now, what else do I know? Well, I know that n has to be perpendicular to v, right? I know that because p and q are on the plane and n is the normal vector, then I know whatever vector I have, it has to be perpendicular. So I know that that normal vector is perpendicular to that direction vector, which means that if I were to take their dot product, I would have 0, right? So the dot product of n dot product with v would be equal to 0. It has to be. All right, therefore, how will the plane work? Well, let's write down that dot product. So plane, the equation of a plane, is using this piece right here. N is the vector a, b, c. So the dot product works a, right, the a value times x minus x0. So a times x minus x0. Right? That's the dot product for the I components, plus b, and then I'll have the component for that, and then c here. I'm just going to try to help my colors along here. Okay, so then this will be y, this will be z, and then this is y0, and this is z0, right? So these pieces are the direction vector. Right? It's very similar in many respects to the point slope form of an equation of a line expanded. If you remember point slope form, it was y minus y0 equals m times x minus x0, right? That's how we had point slope for a line. And if you look, this is very similar, right? We have our y minus y0, we have our x minus x0. We just have another component, z minus z0, and then we broke the m apart into its component pieces, right? And with a direction vector. So that's where the a, the b, and the c come from, because they're from that normal vector coming out. Right? So it's very similar. It's not exactly the same, but that is the equation of a plane right here. The standard form for the equation of a plane. And that's written for us right on the top of the next page. Right? The standard form of the equation of a plane with a normal vector n, which is ABC, that passes through the point P, which is x0, y0, z0, is that equation that we just developed on the previous page. All right, so let's put this into practice. We want to find the equation of a plane through the point 2, 2, 0 with a normal vector n, which is 2, 4, 3. Okay, well, this is easy because they gave us x0, y0, z0 right here, And then they gave us a normal vector, which is A, B, C right here. So that means the equation of the plane, funnily enough, is 2 times x minus 2 plus 4 times y minus 2 plus z, or excuse me, c, sorry, c, which is 3, I was thinking the z component, times z minus 0, like that. And then the whole thing is equal to 0. That is the equation of the plane right there. Yes, of course, you could expand it out, distribute if you so desired. As a matter of fact, I think I'll do that. So it'd be 2x minus 4 plus 4y minus 8 plus 3z equals 0, which would be 2x plus 4y plus 3z plus 3z. And then this is minus 4 and minus 8, which is minus 12, and we'd bring it over to the other side. And we'd have it equal to 12. So there we go. All right, now we want to graph this plane on this vector because they want us to graph it. And this is one type of 3D graph that you are expected and can be expected to do. So one of the things you want to think about is your intercepts. Let's think about this. If I have x-intercept, if I'm on this x-axis, then my y value and my z values are 0. So it would be 2 times x minus 2 plus 4 times 0 minus 2 plus 3 times 0 minus 0 equals 0, right? You'd be putting a 0 in here and a 0 in here for your x and for your y because you're on the x-axis, which would leave you 2x minus 4 and then plus a negative 8, right? Because 4 times 2 is negative 8, so minus 8. And this is 0 over here. 3 times 0 is 0. So sure enough, 2x equals 12, so x equals 6. So your x-intercept is 6, 0, 0. Now I'm writing it as a vector, or you can write it as a point, whichever way you like. 1, 2, 3, 4, 5, 6. It's right there. All right, so that's your x-intercept right there. Now, your y-intercept, let me change to a different color. The y-intercept will have x be 0 and z be 0. So it'll be 2 times 0 minus 2 plus 4 times y minus 2 plus 3 times 0 minus 0 equals 0. So you're putting in 0 here for the x and 0 here for the z. All right, well, that's 2 times negative 2, which is negative 4, plus 4y minus 12, and then that's 0 again, equals 0. So 4y equals, let's see, 12? Oh, I know what I was doing. It's 8 here, but I was making it 12 in my head because I knew this was going to be 4y equals 12, which is y equals 3. So my y-intercept is 0, 3, 0, right there. So on my y-axis, I'm going to go out to 1, 2, 3. And you can see maybe at this point, you can draw your first trace. There's a trace of your plane. Your plane is going to intersect the xy axis, or excuse me, the xy plane at that trace. That's the line where your plane is going to cut across it. So right here is your y-intercept, like that. All right, now we need to know the z-intercept so that we can make our other two traces. We need one on the xz plane right here and one on the yz plane right here. All right, so let's see here. Let me grab another color, one more color. So the z-intercept would be, you're putting in 0 for x and 0 for y. So it's 2 times 0 minus 2 plus 4 times 0 minus 2 plus 3 times z minus 2, or z minus 0. There are so many minus 2's in there. Z minus 0 equals 0. And let's see, this is negative 4 minus 8 plus 3z equals 0. So sure enough, z is going to be equal to, well, 3z will be equal to 12. Z is equal to 4. So it's 0, 0, 4 is your z-intercept. So I'm going to put that right here. 1, 2, 3, 4, right there. And then we can draw our other traces. So you have a trace right here and a trace right here. It's where your plane intersects. Now the plane keeps going on past these values, but this is how that plane cuts across the coordinate axes. So this right here is the XY trace because it's sitting in that XY plane, that horizontal plane. This is the XZ trace. Right? It's where the X and Z plane hits that plane that you are intersecting or you are drawing. And then this is the YZ plane. Right? Again, it's where your YZ plane intersects the plane you're trying to draw. And up here, I forgot to say, that's your Z intercept. Right? When you're drawing a plane like this, it's really wise to find the intercepts, draw the traces. We know that it continues on infinitely because a plane continues on infinitely, but nevertheless we have how it cuts across the coordinate axes at this plane, right? And by drawing these traces in. All right, let's do this next example before we finish this video up. So we want to find the equation of a plane given the points P, 1, 4, 0, Q, negative 3, 1, 1, and R, 5, negative 2, negative 4. And at this point, it helps to remember a little bit from geometry and algebra. So I just want to make a little note. 2 points make a line, but 3 points make a plane. Right? So when we're given 3 points like this, we should be able to make a plane. That's just a little note kind of on the side. Okay, so let's think about this for just a second. We have 3 points. I'm going to draw a plane here. And of course, this is not to scale. I'm not trying to draw this in the coordinate axis system at all. I'm just trying to draw this. So we have a point P, we have a point Q, and we have a point R. Right? They're obviously not in the coordinate system, but this is how they exist. Okay, so let's think here. In order to come up with the equation of the equation of the plane, I need to have a normal vector and a point P, right? So my point P is no problem, right? Point P I've got. It's right here, right? There's P right here. So I know that that's x0, that's y0, that's z0. That's no problem at all. But I'm going to need that normal vector. I need the normal vector that sticks up out of that point P. Well, I have 2 other points. I have Q and I have R. Well, these 2 vectors, whatever they are, that is sticking up out of them. And we find a normal vector sticking up out of them with a cross product, right? So we need to find that normal vector. And let's see, I'm going to draw it in here. The normal vector n would be equal to PQ cross product with PR. Okay, well, let's find PQ and PR. That'll be a good start. Okay, so let's see, PQ, terminal minus initial. So negative 3 minus 1 is negative 4, 1 minus 4 is negative 3, and 1 minus 0 is 1. And I'm going to cross product that with PR. So 5 minus 1 is 4, negative 2 minus 4 is negative 6, and negative 4 minus 0 is negative 4. All right, so let's sneak this cross product in here. So if we have to write the answer in a small version, we can do it. All right, so I, J, K, and I'll just do I and J right here. So we're taking negative 4, negative 3, 1, and we're cross producting it with 4, negative 6, negative 4. Okay, so it's going to be a little lengthy one. Let's see if we can do this. All right, so diagonal, it's 12i, and then 4j, right, 4 times 1, and then 24k, minus, actually I'll put the minus down here, and then going backwards, negative 12k, negative 6i, and 16j. All right, so that means that my normal vector n, which I'm finding right here, is equal to, let's see, 12 minus 6 is 18. And then, let's see, I lost my j. That was a j right there. All right, so negative 16j and plus 4j, so that's negative 12. And then 24 minus a minus 12, which is 24 plus 12, which is 36. All right, so I have my n right here. So there's n. N is that cross product. So then the equation of the plane, funnily enough, all I have to do is combine my n and my point, right? So I should have labeled that one. So that is x0, y0, z0, right up there. So for the equation of my plane, it's going to be the n value, which is 18, times x minus x0, which is 1, plus, minus 12. I did minus because it's really plus a negative 12. So, and then y minus, and my y0 is 4. And then plus 36 times z minus 0. And all of that equals 0, right? It's an equation of a plane, so it has to have an equals on the other side. Now, if you want to complicate, or not complicate, but if you want to multiply everything out and get everything together, it's fine. So it's 18x minus 18 minus 12y plus 48 plus 36z equals 0. So that'd be 18x minus 12y plus 36z equals negative 30, right? Because those two make 30. And if you wanted, you could even divide everything there by 6, right? Because 6 goes into 18, 12, 36, and 30. So you could write it this way, or you could write it this way. All three of those things that are boxed are all the exact, or the equations of the same plane. So it's all the exact same plane, but it's different ways of writing it. And before I leave this behind, I do want to show you that you can do this in Maple. Maple can help you. For one thing, I have the plot drawn from the previous example. That's that plane that we were drawing. And you can fiddle around with making it a surface and whatever, but you can see the traces if you play around with it a little bit. Right? So that's that one. And then if you want to have help with the cross product, of course you can by using cross product. And then you can see I have that plane that we were looking at drawn right there. That's the plane that we were just looking at. Actually, I was wrong. That was the problem for the equation of the plane for the next problem. Here's the equation of the plane that we were looking at right there. So that's the plane that we were finding. So 18x minus 1 minus 12, y minus 4 plus 36 times z minus 0. And of course, I'm using implicit plot 3D to graph these. I named the plane and then I'm just using it to graph it. You just want to make sure you have appropriate x, y, and z coordinates so that you can actually see what the plane is that you're trying to look at, which we can here.